Hi Math 215 students. In this video we're going to have a quick comment on the number of solutions possible for a linear system. So this falls into our big questions about linear systems. In part B's videos we talked about how to solve a linear system. So in a sense, if you just solve a system, you're going to be able to tell how many solutions there are. So you may not be surprised by our answer to the second question. How many solutions does a given system have? But we'll go ahead and just make it crystal clear. And we'll talk about how to figure this out efficiently. All right, so before moving on from this video, here are a couple things that you ought to be able to do. You want to be able to define consistent linear systems, inconsistent linear systems, unique solutions, and non-unique solutions. And you want to be able to describe how many solutions a given system of linear equations might have using that terminology that you have mastered the definitions of. Okay, and echelon form will be very important for answering these questions, so we'll see how that happens. All right, so if we were to just kind of take a poll of the solutions we've looked at in the examples, if we asked how many solutions were possible, here are our examples of equations with two equations with two variables, and if we were to count the number of solutions each of these examples had, we'll see that the first system had no solution because there was no point of intersection. The second example had exactly one solution because there was exactly one point of intersection. So even though our solution consists of two numbers, x equals 2, y equals -2, those two numbers form one single solution. There's one point of intersection. And finally, in this last example, where the two lines actually coincided, they had the same graph, there were infinitely many points of intersection, telling us that there are infinitely many solutions to that system of equations. Similarly, when we saw our examples of equations with three variables sketched as planes in XYZ space, we saw that in some situations you might have three planes that all intersect in a single place, a single point, in which case you would have a single solution. In full generality, you might run into equations corresponding to three planes that didn't ever intersect in a single place. There's no single point that lies on all three planes at the same time, and so that would correspond to there being no solution to a system like that. And some systems, we were told, correspond to three planes that lie having an intersection with actually infinitely many points. All three planes pass through this line I'm tracing out. There are infinitely many points on that line, and so there would be infinitely many solutions to a system whose graph looked like three planes arranged like this. All right, so those answers were the same in our two examples of two equations with two variables and three equations with three variables. And in general, the answer will be the same no matter how many equations and how many variables. For any linear system, there will always be either no solutions, one single solution, or infinitely many solutions. It's either 0 or 1 or an infinite number of solutions. Now we'll see exactly why that is in a second, but let's come up with some terminology to describe what we've just said already. So the new terms we want to introduce are consistent and inconsistent, unique and non-unique. And so what these mean are this. A linear system that has at least one solution is called consistent. If a linear system has no solutions, it's called inconsistent. So the first type of solutions here, no solutions at all, that would be an inconsistent system. The latter two, having a single solution or having infinitely many, these would both be considered consistent systems. Next, if a consistent linear system has just one solution, that solution is called the unique solution. Otherwise, we say the solution is non-unique. All right, so in our possibilities here, if we have no solution at all, it's called an inconsistent system. If there is exactly one single solution, we say that that solution is unique. If there happen to be infinitely many solutions, we would say that the solution is non-unique. All right, with that terminology, let's go back and describe these examples. As you take a look here, you might want to pause the video and see if you can use that terminology in sentences describing the numbers of solutions to each of these three systems. What does the fact that there's no solution or one solution or infinitely many solutions say about these three systems and their solution sets? All right, let's suppose that you did pause the video and you came up with some answers. Let's see how you did. The first system is inconsistent because remember, inconsistent means that there is no solution possible for the system. In the second example, we do have a consistent system because there is at least one solution, one place of intersection, and because there is exactly one place of intersection, we know that that solution, x equals 2, y equals -2, is the unique solution of that system. And finally, the third system is consistent because there is at least one solution, and because there's more than one solution, we'll say it is a non-unique solution. All right. Now, as we take a look, let's look in particular at the inconsistent system and apply our vocabulary there. You'll remember we worked through the details of elementary row operations on this example in Part B's videos, and we saw that doing row reduction on this matrix gives us an echelon form that looks like this, and that second row in particular corresponds to the equation 0 equals -24, which is never true for any x and y, and so there's no solution to this system or the original system. The system is inconsistent. And if you remember what we said, when it happens that you won't have a solution, we said that you will not have a solution if there is a pivot position in the last column of your augmented matrix. So to say that in the same ideas but with different vocabulary, we'll say that a linear system will be inconsistent exactly when some pivot position of the augmented matrix occurs in the last column. So this is the scenario you'll run into when you have an inconsistent system. Moving back to the diet example from our previous videos, once we got to echelon position, we were able to look here at the pivot positions, and we have a pivot position in this spot and in this spot, and that tells us something. The pivot positions happen in each column except the last. That means that we will eventually be able to solve for x2 and for x1 exactly, and that means that there will be exactly one solution. There will be a unique solution. And in general, this is what happens. What you'll want to do is go to the echelon form of your matrix. And when you have arrived at the echelon form, like we have in the middle matrix here, take note of where the pivot positions are located. Remember, that is the location of the leading entry in each non-zero row. It turns out that if you have a pivot position in every column except the last one, remember you don't want a pivot position in the last one because that would mean there are no solutions. But if you do have a pivot position in each column except the last, then the system will have a unique solution. If it just has pivot positions outside of the last column, we know it's consistent, but having a pivot position in each column except the last means that the solution will be unique. Now remember from the previous videos, if you don't have a pivot column in each column besides the last, then that means that one or more of the variables will be free. What happens when you have free variables? Well, when you have free variables, remember that everything else is written, the basic variables are expressed in terms of those free variables, and the free variables are allowed to take on any one of infinitely many different values, and that means that there will be infinitely many solutions. So in this last example we worked on with the electric circuit, we got down to our echelon form, we located the pivot positions there, and we saw that x3 and x5 corresponded to they were free variables, they corresponded to non-pivot columns. And what that tells us is that there's going to be more solutions than just one. So the solution will not be unique, but the system will be consistent. And again, this will happen if and only if there is a non-pivot column happening before the last column. Now, because every column is either a pivot column or not a pivot column, if the system is consistent, you'll have either a unique solution or a non-unique solution. In other words, you'll have exactly one solution or you'll have infinitely many solutions. So that is our answer. How many solutions does a specific given linear system have? The answer is either 0 or 1 or infinitely many solutions. How can we figure this out? The key idea will be to go to find out where the pivot positions are. You'll find the pivot positions from the echelon form of the matrix, and locating those pivot positions and seeing whether they fill every column but the last, or whether they do allow for free variables, allows you to see whether you have 0 or 1 or infinitely many answers. Well, that's the end of this video. Hopefully you'll be able to define these terms and make sure that you can describe how many solutions are possible for any linear system, and then use the echelon form of a coefficient matrix or an augmented matrix to decide whether solutions exist, whether your system is consistent, and whether or not the solution is unique. Well, thanks for your attention. I'll see you in the next video.